Today we are doing a very complex chapter, guys. This is one of the most complex chapters of your syllabus. So a lot of things would be very difficult to understand. So my suggestion here would be that see why this topic becomes very difficult to understand is because it involves a lot of understanding of machine learning. Uh, if you don't have that requisite background, maybe it will take some time to grasp those things, right? So that's the whole point, right? Topic itself is not difficult. It is just that people come from different backgrounds, and when people come from different backgrounds, they are not at the same level, right? For somebody, principal component analysis might seem very easy, but for somebody else, this PCA might seem very very hard, right? So keep that thing in mind when you're preparing for this chapter. If you require, let's say, if you need some additional kind of thing to read this chapter or understand this chapter, let me know. I'll provide you some external document or reference point or something which can make your understanding better, right? So that's the whole point here. Okay, so let's start to dig deeper. We'll try to cover up this machine learning method topic. Very long chapter. I don't want to rush it. We'll try to cover as much as possible in this lecture, two and a half lecture. If there is something pending, right? If we are not able to complete that, then I'll kind of record that in and provide that in the recorded component, right? Because if I start to rush here and complete everything, then that will spoil the whole thing, right? So that's the whole agenda, right? So keep that thing in mind. All right, guys. So machine learning method, very very important. You have the whole objective of studying quants is that you are able to forecast it. You're able to do the forecasting part. And when you talk about forecasting part, I think the last part, the last bit of the quant is that you need to know how to how to forecast, right? And machine learning in
5 red lights in Baku, and the
uh,
Azerbaijan.
Jaydeep, some noise coming, right? So, so that's the point, right? So, the whole point which I want to stress here is that please understand very very clearly that machine learning is the culmination of your understanding of quants. We started understanding your probability. We started understanding your regression, linear regression, multiple regression diagnostic, time series data, simulation and bootstrapping, everything, right? The whole objective of studying all those things was only one, that we should be able to forecast better. We should be able to forecast things in a better way, right? That was the whole objective. Okay, so machine learning is like the final step where we'll incorporate all those concepts and move ahead. Let's dig deeper, guys. So now, so machine learning and data preparation, when you talk about the first part is we'll try to okay, before I tell you this thing, uh, your machine learning methods are divided into four topics, four modules. One is, first of all, the basic understanding of machine learning and the steps in the data preparation. Then we'll learn about your PCA method, principal component analysis, and your K means clustering, right? This K, you have to know what again K means clustering means. Then uh, module 3 is about understanding what are different methods of prediction and how do you do sample splitting. Module 4 is again advanced method of your reinforcement learning as well as your natural language processing, NLP, right? So very very advanced topic. Let's go ahead. Okay. All right, guys. So in this part now, we will focus on your understanding of three subtopics, right? When I talk about three subtopics, what do I mean? Your machine learning and data preparation has been further subdivided into understanding of machine learning versus your classic econometrics. Then the second topic is difference between supervised learning, unsupervised learning, and reinforcement learning, right? There are three kinds of different parts in your machine learning. One is supervised learning, one is unsupervised learning, one is reinforcement learning, and finally, the thing is your data preparation and your data cleaning, right? So keep that thing in mind. Now let's dig deeper, guys. Okay, the first part here, listen to me very carefully, guys. The first part here is we are trying to understand the difference between your machine learning versus your classical econometrics, right? See, as I told you, right? Ultimately, when you think about machine learning is what? Machine learning is all about forecasting and prediction, right? You are basically building your models to recognize your data patterns for your practical applications. So once you have that understanding, things become quite easy. Okay. Uh, Overall, if you think about your classical econometrics also, econometrics, the classical one was also on the similar lines. We were looking at your economic or the financial theory, which kind of drives your data generating process, right? So what has changed from machine learning to classical econometrics? So if I have to give you a kind of a simple summary, right? If I have to give you a simple summary, that uh, machine learning is your data driven and your prediction first, right? So basically you are using flexible models, you are using models which incorporate your trees, your nets, your ensembles, and you do the cross validation to maximize your out of sample accuracy, right? When you talk about classical econometrics, it is different. It is your theory, it is your inference first, right? You use your different models where you look at your ordinary least squares, your time series to estimate your parameters, test your hypothesis, and you try to identify the causal effects, right? So these are the things we need to understand. And if you think about machine learning, that what is machine learning, how it works, what are the strengths, what are limits. So overall what you need to know is that machine learning works very well on your new data, right? If you have new data, right, then it is one of the best things which we can use, right? Because the primary metric in your machine learning is your out of sample data, right? So out of sample performance, not whether coefficients are statistically significant or not, right? It is about your out of sample data, right? So if I see, this is the initial slide. So we are looking at things at the high level. You use your large set of features, right? You use your large set of features here, and what you do here is that uh, possibly those features could be thousands or more than that, right? That's why we have written that you have large data volumes, right? That's what we have. And you try to have your flexible functional form, like your decision trees, your random forest, your gradient boosting, your neural nets. These are all types of machine learning models, guys, that can capture your non-linearities and your interactions automatically. What you also try to have is you try to prevent the overfitting, right? How do you try to prevent the overfitting? You try to prevent the overfitting with your cross validation, regularization. You use your uh, models such as lasso and ridge, we'll study ahead, and you try to have early stopping and ensembling. Then we look at your tuning of the models. You tune the hyperparameters using your validation curves or the what are critical values if you want, right? So these are the things which you need to understand. Is that first thing? I know this is very tough if you don't have the background. So the point here is you first of all keep in mind that you have to use extremely large data volumes. Then you also need to have flexible functional forms, right? Flexible functional flexibility and your wide range of specification. You have to uh, try to capture your non-linearities. You have to prevent your uh, overfitting, right? That's what. And you kind of tune the hyperparameters. What are the strengths of machine learning models? When you look at the strength of the machine learning models, please keep in mind machine learning models have excellent predictive powers with lot of data and features. It try to automatically captures your complex, your non-linear relationships and interactions, and it is very good model to scale to your big data, your high dimensional inputs, your unstructured data, etc., etc. So overall, please keep in mind that when you talk about machine learning, we have a lot of things inside machine learning: your supervised learning, your regression, your classification, your unsupervised learning, which is your clustering, your PCA, your boosting, bagging, deep learning, embeddings, etc. Right? So these are the things we need to understand. Again, this is the first slide, so just keep a overall perspective in mind, and also understand that when you have such kind of models, right? There are certain limitations also, right? Because you're dealing with big data sets, requires a lot of data and compute power. You have less emphasis on your interpretability and your causal identification, right? And so these are the things which you need to keep in mind. Now, I've given you a broad understanding of machine learning. What you need to also understand is your classical econometrics. What are those? How do they work? What are the strength and limit? Please understand when you talk about your classical econometrics, you understand and estimate your relationship between variables with your emphasis on your inference and your causality, right? So you are more focused on, does X causes Y, right? So you focus more on that, okay? And guided by your economic, your financial theory, right? So you're backed by your economic or financial theory. That is more important in your econometric. You specify a model, often your low dimensional, you based on your theory, whatever it is. You have different equations here. You use your estimators with your ordinary squares, your fixed effects, your ARIMA model, your GARCH model. You test your hypothesis with your t-test, your f-test. You construct your standard errors, your confidence interval, whatever you have learned till now, right? Whatever you have learned, all those tests, right? You do that. Use your different strategies and common method I told you, right? OLS, your panel data, your ARIMA, GARCH, etc. And when you do all that, right, ultimately uh, you look at your strength of this model, right? If you think about the strength of this model, there is clear interpretability. Coefficients have economic meaning. Methods are aimed at your causal inferences. You look at correlations. You look at statistics. You look at unit roots. You look at heteroscedasticity. You This thing works very well with your smaller data set where you're looking at asymptotic theory and identification things. So all of these things are part of your classical econometrics. Sometimes, if you think about the limitation of classical econometrics, those things might be misspecified if the two relationship are non-linear or very complex, and you often need your very strong assumptions like linearity and etc. here, right? So overall, I have given you a clear-cut differentiation between your classical econometrics and your machine learning. So I can write it down also. See the point, I'll write down on the both sides, you will get the idea. See, if your primary goal, right, what you need to understand very clearly, if if you look at the primary goal of machine learning and the primary goal of your classical econometrics, right? I'm writing like this. If your primary goal, see, the primary goal of machine learning is what? Primary goal of machine learning is prediction and accuracy. The primary goal of your classical econometrics is not prediction or accuracy. It is your inference and causality.
But Sudhanshu, one question, sorry for interrupting. The Arima, all the methodologies what you have just stated in the classical economics,
Mhm.
that is also a prediction, right? That is also a part of what we call it a machine learning.
Yeah. See, that is also, but it is the approach which is different. Na? It's the approach. One place we are focused on causality and understanding. One phase we are focusing on inferences. Right? Like, one phase causality and inferences. One phase we are focusing on your prediction accuracy. You just let me write it down. I think that will give you more idea. So if you look at
Sure, sure,
your
sure.
model selection, it will be clear. Don't worry. If you look at model selection, here your models, whatever you select in machine learning, are data hyperparameter driven. Hyperparameter driven. Okay. If you talk about your classical econometrics, here you are backed mostly by theory, right, and your hypothesis, HT, hypothesis testing, right. If you think of the functional form, right, functional form, this functional form here is quite flexible because since you are using a lot of data, flexible, often it is non-parametric, right. Here it is generally parametric formula, right. That's what your ARIMA etc. model comes, right. Okay. Data needs, if you talk about data needs, here data is needs requirement is large, right. Many features, right. In this part, in the next part, you can work with small data. Okay. Then if you think about your use cases, right, use cases you think about, so machine learning is used in your scoring method, in your forecasting, your pattern detection, right. This is used in mostly your, what do you say, policy evaluation, right, causal estimates. Okay. Overall, right, before coming to your answer, your point here is that you use machine learning, okay, when your main goal is accurate prediction. When you're looking at accurate prediction and accuracy, like your credit scoring, your short term price forecasting, your fraud detection, when you have many different predictors, when you have your non-linearity, or when you have excessive data and you want to validate heavily with your large holdout data, that time machine learning works perfectly fine. In case when you need trustworthy parameter estimates, you need a causal kind of claim. What is the effect of your policy on something, or interest rate change, or trading rule change, right? When theory specifies what to estimate, then you use econometrics. Now your question is that, are they totally different? No, we can combine them also. The common best practice is to use your machine learning for your feature discovery, right? Selection and your forecasting, right? Methods, and then use econometric methods for causal estimation and interpretation, or use causal machine learning techniques, right? For example, that's why I told you, right, this topic is very complex, guys, so I will not rush here. Even if I have to record later on, I'll do it, but please try to understand, right? It's very complex. So let's say I'll give you an example, right? uh, if you have credit scoring, right? So in credit scoring, you have machine learning, your XGBoost, your neural nets. You use, why do you use that? Because you want to have your high accuracy. But now regulators may demand your interpretability. Regulator may demand your stability check, right? Then you have to combine that machine learning model with your transparent features and your explanation tools, right? So that's what you have to do. Now let's say you have to estimate your beta or the cost of capital, right? Now here your econometrics will work fine because you're looking at time series regression, because coefficients are your interpretable and theory driven. When you go to your algorithmic trading, when you go to your HFT, right? Then there, what is the requirement? There in the shorter time frame, the requirement is your pattern detection. The shorter time frame requirement is that you're looking machine learning for ticks, data from the ticks, right? News embeddings, heavy emphasis on out of sample back testing, etc. So you will use machine learning. And let's say you are doing stress testing or model validation, then econometric test and diagnostics are required. So machine learning model must be subjected to your additional validation or whatever, right? So in your modern world, we are using hybrids. In a modern world, we are using your causal machine learning. We are using there are a lot of things you will see ahead, your regularized regression, your lasso, etc. Also, so that we use. So please understand that it is not in isolation, right? You, like you were saying, that we use time series also. It's not in isolation, right? So we have embedded systems also, we have dual systems also, we use both of them together also. Ultimately, it depends on what do you want. Whether you are looking for only prediction and accuracy, machine learning. Whether you're looking for causal inferences, casual classical econometrics, right? You check the sample size. If the sample size is very very large, in that case, you'll go for your machine learning. If it is small, you go for your this what you say, you go for your classical econometrics, right? So you check the sample size, features, etc., etc., right? Overall, please understand, like machine learning is a very powerful, flexible predictor, best for your large data, your complex patterns, right? All those things you use. Whereas you use complex things, you use machine learning. But when you have the principled or inferences kind of things, causal claims, theory testing, you use your uh, what you say, classical econometrics, but you use them combined a lot, right? So that's the first slide, guys. Moving on, next part we have to discuss is, okay, practice question, right? Compared to traditional statistical methodologies, machine learning provide all of the following except what, guys? Tell me. Machine learning definitely provides greater flexibility, right? So it is not except. There is no need to scale the data, right? Tell me. The ability to manage large volume data, that they do. The capacity to capture non-linear transaction, right? Machine learning do that non-linear transaction, yes or no? Right? Tell me. It's a benefit, na? Machine learning is able to capture the non-linear transaction, right? They're all, pattern recognition. It will be able to do, right? Non-linear, right? So only thing is there is no need to scale the data, right? Except no need to scale the data, because we need to, this is not part of your, uh, what do you say, benefits, right? No need to scale the data. I think this is the answer. Yeah, B. Many machine learning methods requires the need to scale the data, right? I told you, right? Require the need to scale, right? Common techniques for doing so include standardization, normalization related to your traditional statistical models. Machine learning models, greater flexibility, which I told you, can manage large volume data, I told you, can potentially capture non-linear transaction, I told you, right? So that's what it is. So it's a question is straightforward. All right, guys. Now we are going into much more complex thing, guys. The next topic here is your understanding of your supervised, unsupervised, and your reinforced or reinforcement learning method, right? That is what we need to understand. Uh, See, when we talk about your supervised learning and unsupervised learning and reinforcement learning, first we need to understand that all three are used for different kind of reasons, right? Different kind of works, right? So supervised learning, as it is given in your slide, right? Supervised learning is used to predict the value of a variable, example your car value, or classify an observation, sports game outcome, etc. Unsupervised involves your pattern recognition in data with your no specific target, and reinforcement learning incorporates a trial and error approach for decision making in a changing environment. Let me kind of dig deeper now in this, right? Supervised learning, please understand the first one. Supervised learning is like learning a mapping from inputs, right? So you have your labeled outputs. From your inputs you get label outputs, right? You try to predict or classify. Unsupervised learning finds a structure inside your unlabeled data, right? So supervised learning, you are mapping from inputs, and then that is labeled outputs, predict and classify. Unsupervised learnings, you are finding your structure inside your unlabeled data, which can be clusters, your low dimensional structures, your anomalies, etc. And then you have reinforcement learning, which where you uh, learn how to act sequentially to maximize your cumulative reward in a kind of environment, right? So you will understand, guys. Just hold on, right? This is a complex topic. When you talk about supervised learning, right? See, supervised learning, the goal is what? The goal is to predict a target given features, or let me write it down. Supervised learning, what happens is that supervised learning, when you talk about supervised learning, right, the target is or goal is predict a target y given features x. Okay, predict a target y given features x. And in this, right, in your supervised learning, we have again, you have label data, right? Algorithm learns using your label data, whatever value of car features, car make, model, year, size, engine, etc. Can predict variable values in time series or cross-sectional scenarios, right? Common algorithms in this is your linear regression, your logistic regression, your uh, regularized linear models such as your ridge, your lasso, your tree-based decision tree, which is random forest, your gradient boost, your uh, support vector SVMs, your KNN, neural networks, etc. Right. So overall, what you need to know here is that in supervised learnings, we are focused more on label data, right? And we are looking at prediction, which is across time series or cross sectional scenarios, right? In finance, if you talk about, you have credit scoring, you have loan default prediction, you have short term price forecasting. Those are the things we have, right? Then the next part, right? We have unsupervised learning. Unsupervised learning, the goal, if I put it, unsupervised learning, ULI, let me write UL. The goal here is discover your structure without labels. Okay. So when I talk about discover a structure without labels, what exactly do I mean? So it may involve your data clustering, identifying a small group of explanatory factors. It is not used for prediction, but useful for characterizing and learning your data set structure, which I told you, discover structure without labels. An internal auditor evaluating a company transaction to identify areas for review, right? So what happens here is that whenever you have to do, let's say, customer or investor segmentation, whenever you have to discover your regimes or latent factors, whenever you have to discover your fraud detection or unusual transaction, whenever you have to do pre-processing to reduce your dimensionality, right? So in that, all those cases, unsupervised learning is used. This is a method where no, uh, kind of, if there is a cluster, you validate the cluster with samples, etc. So it's basically a pattern recognition exercise, which you use in data with no specific target, right? Then you have reinforcement learning. When I talk about reinforcement learning, the core idea is that there is an agent that interacts with an environment over time, and as the time passes, at each step, it observes, let's say, a state ST and chooses action AT, right? And then it receives a reward, and next stage again it moves to a next stage, right? So the goal here is to find a system where the reward happens, right? You incorporate a kind of a trial and error approach, and you have a, when you make a right decision, you get a reward. When you make a wrong decision, you are penalized. So you have a trial and error approach for a decision making in a changing environment. It's often used in risk management of large block trading, because there you want to make a decision very fast, right? So that what we need to keep in mind. So execution algorithms, your portfolio rebalancing, right? Market making, your dynamic hedging. So reinforcement learning is very active in your live markets. You are using live markets, you need careful back testing, robust risk control, all those things. Okay. So overall, if you want to understand these three things very clearly, please understand that your supervised learning is all about data. Supervised learning needs your labeled outputs. Unsupervised learning needs nothing, right? Reinforcement learning needs your environment and reward signal. So reinforcement learning needs environment and your reward signals. Okay. Objective of supervised is to, let's say, map. It's the objective of supervised is to map your X to Y, right? Uh, Unsupervised is all about your structure. Here it is all about understanding data structure, right? Representation. Reinforcement learning is your sequence of actions. It is your sequence of actions. Okay. In those sequence of actions, right, which are maximizing your what long-term reward. Okay. Overall, be very clear that these are three different methods in your supervised and unsupervised learning. Your data is generally IID data, your independent and identically distributed data. Reinforcement learning, you're basically dealing with, you know, dependency, right? You have temporal dependency and delayed feedback. So again, I can go on and on these things, but overall, have an idea that if you want to map something, follow supervised learning. If you want to understand data structure, follow unsupervised learning. If you want to have actions where you get rewarded for correct decision making and you got penalized for wrong decision making, and you want to test in the live market, you want to develop something for that, that's a reinforcement learning you have. Okay. Again, I'm telling you guys, these topics are very difficult to understand, so I'm trying to make it as simple as possible, but again, not so easy to get a hang of it, right? So keep that in mind. All right. Next point here, when we try to understand here, is your the compliance manager is a practice question. The compliance manager at a bank uses machine learning approaches to review the journal entries posted to bank's general ledger. In particular, she is concerned with employees using the wrong ledger accounts to record the transaction, right? So, okay, that's fine. Wrong ledger accounts to record the transaction. This type of machine learning is best characterized as what? See, here you are doing what? You are worried about your employees using the wrong ledger. Right. So listen to the question again. The compliance manager at a bank is using a machine learning approach to review the journal entries posted to the bank's journal ledgers, right? And now, in particular, she is concerned with what? She's concerned with employees using the wrong ledger account to record a transaction. Now, the question asked here is that what type of machine learning it is part of, right? Whether it is part of supervised, unsupervised, reinforcement, or linear regression analysis, right? So that's what we need to guess, right? First of all, when you see such kind of question, you should have a mental map that you try to figure out that, okay, what exactly happens in supervised, what exactly happens in unsupervised reinforcement. See, it's not a reinforcement because there is no decision making happening, right? So I am very clear that there is no reinforcement, there is no linear regression analysis. So my now decision point is only two, right? Whether it is a supervised learning or unsupervised learning, right? So the point here is, what is the goal here? The goal is to detect patterns and anomalies in what? It's a labeled data or unlabeled data, right? It's already an unlabeled data, right? Why I'm saying it's unlabeled data? Because it is not saying the entry is right or wrong. Since it is not giving right entry, wrong entry, anything, right? So it's a unlabeled data. Now, if you have unlabeled data, which learning you use, guys? Labeled data is supervised. Unlabeled data is
Unsupervised.
unsupervised, right? So my point is, see, in this kind of topic, you have to be a little smart. You cannot understand everything, but if you are a little smart, you understand that, okay, unlabeled data, there is clustering, there is anomaly detection, there is a all those things you have, you want to match what the manager wants. So that's a unsupervised learning, right? So So that's easy to, right? So it's unsupervised learning. Unsupervised learning is used in your situations like this, where a compliance manager wishes to learn about the data but is not using it for predictive purposes. While supervised learning and reinforcement learning are established methodologies, linear regulation is not an applicable machine learning category, right? So that's what we have, guys. Moving on. And next is data preparation and cleaning, guys. See, machine learning looks a very fancy term, but ultimately, what we need to understand in all the machine learning part is that machine learning is the first and the basic part in machine learning is data cleaning, right? If you can't do data cleaning right, you cannot get the desired result, right? Your ability to get the desired result goes down drastically if your data is not clean. And that's what is discussed here, that you need to prepare your data, you need to clean your data. If you're talking about preparation and cleaning your data, to the two primary methods to achieve your scale consistency, right, is standardization and normalization, right? So that we need to have. What is the standardization? You used to create scale for measuring your variables with zero mean and unit variance. That's what we know. Preferred methodologies for data converting a wide scope. What you do is you use a method of your standardization. Standardization is basically your Z score, right? If you remember the Z score which we had discussed, Z score rescales your features to zero mean and unit variance. Then there is a normalization. Normalization means your min max, right? Min max kind of thing, and it rescales to a fixed interval, often which is between 0 and 1. So, and data cleaning is basically about fixing your missing values, outliers, your duplicates, your inconsistent formats, your irrelevant rows, so models can learn your true signal instead of your errors. Okay. When you talk about your scale consistency, which is the standardization, right? So it's basically the Z score. Z score is you subtract your mean value and divide by your standard deviation. Then you also have another normalization which you do, right? Normalization is that you are trying to take the min max value, and you are finding out. And overall, the point here which you need to understand is that the the reasons are given, right? The missing data, outliers, duplicate observation, inconsistent recording, unwanted observation. Because when you have all these things in your data point, right? So the whole thing is that you get, if you have wrong data, right, it's garbage in garbage out kind of thing, right? If you have wrong things in your data, right, you will not get the correct result, right? So this is a pretty straightforward slide. I don't think there is anything to learn here, right? Moving on, guys. Okay, now we are moving to your module 2, right? In module 2, so module 2, when we go, basically here we'll talk about your two things. But in your PCA, principal component analysis, and other is your k-means clustering. Okay, both are two different techniques. Both have two different methods and advantages, disadvantage. We'll see one by one. Right, PCA you have already seen. I think principal component analysis you would have some idea if you have read the chapter, especially the November batch. If you have read the chapter, your modeling of your non-parallel interest rate, there we have discussed a little bit about your PCA method, right? So again, some idea is already given there, but still try to go much deeper. Okay, so PCA, right, principal component analysis. This is a very famous technique, very important for your exam perspective, because this is a technique which is discussed, I told you, in the last chapter of your fixed income, which is in the book 4, right? There is a chapter called modeling of non-parallel interest rate. There it is discussed. So it is discussed there. It is discussed here, right? So it is obviously quite important from the exam perspective. What you need to understand is that when you talk about PCA, right, in PCA, what is the purpose of your principal component analysis? Basically, you're trying to analyze your principal component. What are principal component? Principal component are, it is said that uh, for any analysis, there are always 2-3 components which are able to explain the 99% of variation, or more, or at least 95% of the variation of the your independent of the dependent variable, right? your you know your independent variable is able to explain the 95% of the variation of the dependent variable. So PCA finds a small number of orthogonal linear combination of your original variables that capture most of the variance. Basically, what it does is it compresses your data while preserving your information. In practice, you use it for different works, right? Uh, Intuitively, if I have to answer that, what PCA actually does, if somebody asks you in a very simple word that, what exactly is PCA, right? So imagine your data as points in a high dimensional cloud, and PCA finds a new set of axis direction through that cloud such that the first axis PCA goes in the direction of the largest variance, which is most spread. The second axis PC2 is orthogonal to the first and explain the next largest variance. So overall, we are trying to find out your principal component PC is a linear combination of the original variables. You are projecting the data onto the first few PCs, and you're trying to find out what are the most important things which are able to explain the variance in the your dependent variable, right? That's what we are trying to do, and the goal is to what? The popular statistical technique for dimension reduction in unsupervised learning models, guys. Please remember this part. Goal is to produce almost the same amount of information using a small number of uncorrelated components. Uncorrelated, guys, not correlated, that a large number of correlated components can provide. So what you are doing is you are moving from correlated to uncorrelated, and the application here is you are trying to, in this kind of thing, you're trying to reduce the number of features in a machine learning method, often applied to your yield curve movements to describe them with a small count of uncorrelated component. You have observed components should be linear combination of variables. Two most important explanatory components are parallel shift, all rates moving the same direction, and your twist, your short-term and long-term rates moving opposite direction. So first three components, you know what I told you, right? Few components can explain 99% of yield variation over your 10 years due to high correlation. So what we have seen is that three components alone are able to explain 99% of your variation, and that is what is the aim, right? Instead of having large number of correlated variables, we are looking to find three or maybe a little more four principal components which are able to explain 99% of the variation of the whole thing. Right? Three components give the highest number of variation. So what we are doing is, instead of having a large number of correlated variables, we want a small number of uncorrelated variables which are able to explain the high variation, right? So again, a tricky kind of stuff, but intuitively it is very easy to understand, and this is very important for exam because this is what is done used in your modeling of your non-parallel interest rate also. Okay. The end goal of principal component analysis PCA is the use of which of the following to manage dimensionality. Small number of correlated component? No, we want uncorrelated. Correlated, wherever is correlated, go uncorrelated, right? So this is C. Small number of uncorrelated components, right? This is large number, we don't want it. Small number, right? C is the answer, right? So again, I'm giving you much more than what is required. At least remember, right? This is what we have. The goal of principal component analysis is dimensionality reduction. Dimensionality reduction means you are reducing the number of variables. So a large number of components will be, small number of components will be the output. The components should be uncorrelated. So as correlated components do not independently add much value, right? So uncorrelated we want. So this is done, guys. Next is again tricky. Now we are getting into your uh, k means clustering, right? So when you talk about you know k means clustering, again, uh, we need to understand what k means clustering exactly, like what is given in the slide, right? We need to be very clear about it because uh, if you go deeper, right, if you try to go deeper in k-means clustering, it is a big topic, right? We don't want to go that deep. We want to maintain a balance of depth as well as preparation for our examination. So what you need to understand is, when I talk about your k-means clustering, it is a type of your unsupervised learning or no labels, right? The previous one, PCA, was also what? Unsupervised or supervised learning? Unsupervised. PCA was unsupervised. K means clustering is unsupervised. The purpose of this K means clustering is that it group your similar observation, your data points into your K clusters, where each cluster is defined by its center of mass or centroid, right? Why do we do that? Why the whole exercise is done? The whole exercise is done because we want to minimize within cluster variance, and we want to have a system where it points in a cluster should be as close as possible to their center of mass or centroid, because if we get that kind of thing, right, we will have a cluster, right? K means cluster, right? Overall, K is the number of clusters chosen by any analyst. K is equal to 3 for, let's say, 3 clusters. Then you have your centroid or the center of mass, which is the mean position for all points in a cluster. Then you try to measure the distance, how closeness is calculated. So there is a formula for Euclidean distance, right? Euclidean distance, which is given that straight line distance. Euclidean means the straight line distance, right, between your two things, which is calculated your between 2 points, and then there are different formulas. Overall, please understand K means clustering algorithm. What do? Is you choose K, which are the number of clusters. You initialize centroids. You randomly pick your K points or your K means for the smart initialization. Then you have an assignment step, your update step, and you repeat the steps, right? This is the algorithm, which we don't need to get into, right? Overall, please understand that uh, there are different applications of your K-means clustering. You're using K-means clustering for marketing, your customer segmentation, your grouping behavior, grouping customers by behavior, your financing, your grouping stocks with similar return patterns, right? All those things, anomaly detection. If you look at the strength of K-means clustering, it's simple and fast method, works well with your uh, well well separated cluster, easy to interpret. But the only point here is that you need to predefine, right? You need to uh, have a predefinition of K. It is sensitive to your outliers. Your different centroids can cause a problem. If clusters are not spherical, that's also a problem. So you overall, right? See, it's again a difficult method. That's why I told you, right? Teaching this topic is quite difficult because not everybody has got that background, right? In this chapter, right? Overall, what you need to understand is that K means clustering divides or partitions your data set into different groups, right? By minimizing the distance between points and their cluster centroids. It's unsupervised, it is distance based, it is simple, it is widely used for discovering your hidden patterns, like your what I told you, your stock cluster, your customer segment, your transaction group, etc., etc. Right? So that we need to do. But ultimately, if I had to write very small thing which you can help you to understand, please note your K means clustering partitions your data set, right? Partitions your data set into K groups, right? By minimizing the distance between, right, points and their points and their cluster centroids. Okay. Why do we do it? Because it's a way of your unsupervised learning, right? You are looking for your data structure, your patterns, and you want to identify that because you want to do customer segmentation, your stock cluster or transaction groups, right? And when you want to minimize the distance, this is the way you calculate the distance. Even though nobody will tell you to calculate, remember the theory. Nothing else. Goal is to minimize the distance between each observed point and its centroid, right? That is what we do. Okay. So next one is, I think there's a question now. No, okay, not question. Now, what we are doing is in this slide, we are going into much more deeper, guys. We are, you know, what we are doing in this slide is that in this slide we are talking about your inertia, your lower inertia, determining optimal k, what are the scree plot, what is the siluet coefficient, right? These are very difficult topics. I'll try to, or I want to make it a little simpler and easier to understand, just as per the FRM perspective, not the tech perspective, right? So that's what we need to understand. So keep that in mind. First, let's look at the inertia, right? When I talk about your inertia, inertia is basically your measure of distance between each data point and its centroid, right? It's a measure of distance between each data point and its centroid, right? So it's the total distance of all point to their cluster center because we are doing summation. So that is what we have. Think of it as how tightly the different points stick around their cluster center. If you have lower inertia, it means you have tighter cluster. If you have tighter cluster, means you have better grouping, right? But also understand that inertia always falls when you add more cluster because more centroids uh, are easier to fit. So if we blindly add your cluster, inertia will always look better. We need a way to uh, kind of stop at the sweet spot that we need to know, and how to pick the right numbers of cluster optimal k, because again we have two tools here, right? One is your scree plot, we have one is your silhouette coefficient, right? Scree plot is also known as elbow method, right? Elbow method. What you do in scree plot is you plot your inertia, right? You plot your inertia versus number of cluster, right? You plot your inertia versus your number of cluster, and once you do that, right, the curve always slopes your kind of downwards, but at some point it kind of bends like an elbow, right? You see it slopes downward and sometimes it like bend like an elbow, right? And when we talk about bending like an elbow, before the elbow adding cluster gives big improvement. If you are adding before the elbow, it gives you big improvement. After the elbow, right, if you're adding cluster here, right, this part, right, doesn't reduce inertia much, so there's a diminishing return. So if you think about what is the optimal k, right, what is the optimal cluster I want, right, optimal k where the elbow is, right? So simple, in the FRM terminology, if I have to talk about, uh, look at it like diversification benefits in the portfolio. If you're adding your asset, it helps a lot at first, but later each extra asset adds very little risk reduction. So try to add your k here on the top part, not on the bottom part. Then we have silhouette coefficient, which measures how well each point fits inside its cluster versus the next closest cluster. The value of silhouette coefficient lies between your this value lies between your -1 and +1. If you're close to 1, right, if you're close to 1, right, point is well placed. If you're around 0, right, point is between clusters. If you are negative, right, point might be in wrong cluster. So this is another method, guys. This is another method where you are using the value. If you're looking at average silhouette across your all points, right? You choose your K with the highest silhouette score, right? You choose the K with the highest silhouette score, and again, it is like a risk-adjusted return. not just looking at your return, which is inertia reduction, but also how cleanly separate the group or the cluster are. Putting it kind of all together, please understand that when you talk about inertia, inertia tells you the fit. It tells you the fit, right? What do you want? Lower is better. Lower the inertia, better it is, right? So lower is better, right? Then we have your scree plots, right? Scree plots. Scree plots are different. It shows where adding more clusters, right, stops being useful, right? Adding more clusters stops being useful. So this is where it was, right? If before the elbow it was useful, after the elbow it was not useful, right? And then your silhouette coefficient tells you if clusters are well separated. Silhouette coefficient tells you well separated. Okay, together they prevent you from blindly adding your cluster just because inertia is falling. From a FRM perspective, please understand these method comes up when we focus on the unsupervised learning in the risk management. You look at the customer segmentation, your portfolio clustering, your fraud detection. FRM wants you to know that we want if your inertia is basically your compactness of the culture, we want compactness of the cluster. We want your uh, minimum, right? We want your what minimum inertia, right? We want compact cluster, right? So inertia tells you about your, let me write it down again, these things are very complex, guys. Inertia tells you about your cluster compactness. So what do we want? We want lower is better. Scree plots is a elbow method. This is a scree plot, which is the elbow method. And here, if you are adding k before the in the top part of the elbow, it's good. If you are adding after that, not good. Silhouette is the separation quality of cluster. Silhouette is your separation quality of your clusters. Okay. Overall, if you are not able to understand anything, because I understand this is very complex, please keep in mind that inertia should be lower. Your lower inertia means tighter cluster. You always, want that, right? Scree plot, elbow tells you when to stop. Silhouette, how cleanly separated the groups are, right? So that's what we do, right? So overall, we learned about K means clustering. We also learned about how to find the optimal level. What exactly K means clustering do? It's a algorithm to separate your dataset observation into clusters to identify your what you say dataset structure. You have a cluster method which we use. You partition your dataset into different groups by minimizing the distance between points and the clusters and points, right? So that's what we do. Again, this is an algorithm in unsupervised learning that we need to know. Okay, let's try to do a question here, guys. In this question, the optimal number of centroids can be found by choosing what value that provides the lowest possible inertia, right? Yeah, we want the lowest possible inertia, right? We don't want highest possible inertia, that we don't want. So I keep this one. Point where inertia declines at a faster pace as k increases. Points where inertia declines slower pace, right? These two, A and C, right? Which of the option it is, guys? Because your C is also your scree plot, right? So optimal number of centroids can be found by choosing the point where inertia declines at a faster pace as k increases, or value that produces the lowest possible inertia. Tell me, guys. Point C is your scree plot. C,
Assume A.
right? It looks like C, right? Because we can't have, you know, you have inertia and K that we understand. right? Choosing the lowest possible inertia is not the correct method, right? Because see, we want lowest possible inertia, right? But ultimately, if you go back to your slide, right? If you go back to your slide, determining optimal k is scree plot or siloid coefficient, right? So that is scree plot is the answer, right? Which is your this part C, right? Scree plot is the answer, right? D is the answer, right? D or C should be the answer, right? Point where inertia declines at slower. Okay, both are same. Inertia declines at a faster pace. What is the will be the point where slower pace of gain greater than the okay, okay, fine. See, ultimately this was not fine. Small mistake, right? So this is not there that we identified. Ultimately, see, I answered point where inertia declines at a faster pace. So what does your book says, right? What do your slide says? Slide says is that used to calculate inertia for k values, right? And the elbow where inertia declines at a slower pace as k increases represents the optimal, right? So here this represents the optimal number, right? This represents the optimal number. So where the inertia declines at a slower pace, right? So just look at it carefully, guys. Right. So answer is D. Scree plot, remember, siloid, remember, guys. Right. So this is done. Okay. D is done. Then now we are moving to module 3. I'm not sure if we will be able to complete module 4 or not, but we'll try to complete as much as possible in next 45 minutes, 1 hour. We can see. Okay, module 3 is about your methods of prediction and your sample splitting, right? So again, since we are doing the prediction and forecasting, we need to understand that okay, what are different methods of prediction, and we also need to look at your underfitting and overfitting of the models, right? So that's one thing which we need to be very clear. And then when we look at a data, right, when we look at a sample, we need to understand the training, validation, and how to test your data and the subsample, right? So these are also important parts of your machine learning, because unless you are able to do these things on your data, you can't do the machine learning part. Okay, so let's start ahead, guys. Now we are talking about underfitting and overfitting, right? This is not very difficult, guys, because this is quite simple, right? So when you talk about underfitting and overfitting, basically we are talking about whether the model is you know uh, too complex or too vague, right? So overfitting occurs when the model is too complex, right? When we have included more than the necessary variables, we have taken many large variables, etc. Too many parameters, right? So that is overfitting. When you have overfitting model, it is a greater risk or machine learning models due to typically limited parameters in your conventional econometrics model, and it is evident when new data causes the model to kind of perform much worse, and it results in a what you say a training set with a very low error, but with poor performance on data outside the training set. Please understand, when you have a training set, it is working fine. Training set, it works with low error. But when you go to out of sample prediction, right? Out of sample prediction, then the performance turns out very bad. So if you see such kind of behavior, it means that you are suffering from overfitting, right? So you're characterized by low bias, but your uh, there is a high variance in your prediction, right? So model is too detailed, captures even the noise in the training set, looks perfect on your historical and training data, but performs very badly on a new data, which is very poor generalization. Think of it, let's say there is a hedge fund strategy that fits perfectly into your past return, but what happens is when it goes to the new data, it kind of collapses in the future. So very low training, very high test error, bias variance trade-off, which we have studied in FRM, part one chapters, low bias, high variance. Okay, so in simple words, overfitting is, if you have to, I have to just give you one word, it is like memorizing the textbook, right? There are some students now who memorize the textbook. So when you memorize the textbook, what happens? You pass the practice test. But when you get an exam like GMAT, etc., which is, the questions are thinking your logical understanding, you fail the real exam, right? When you go to auto sample test, you fail it, right? So we don't want memorizing the textbook. We don't want that. That is not what machine learning is. So that's not what we want. Okay. So that's what we need to understand. And then next is your underfitting. Okay. Next is your underfitting that we need to keep in mind. When you talk about your underfitting means you are keeping it too simple, right? Occurs when a model is too simple. Now, model is when too basic, right? Very, very simple, too basic, fails to capture relevant patterns. Predictions are inaccurate both in your training and in your auto sample data also, test data also, right? So that's also we have, and misses your important relationships in the data, uses a straight line to model the quadratic relationship between hedge fund performance and your asset under management, right? So what is the symptom here? Excludes your relevant factors leading to bias prediction with low variance, right? Greater risk in conventional models. And look at a bias variance trade-off. Please understand the size of the machine learning model determines if it is appropriately fitted, overfitted, or underfitted. If it is underfitted, it is high bias, low variance. If it is overfitted, it is low bias, high variance. Think of your underfitting as, if overfitting was proper time memorization of textbook, underfitting is you are not studying enough, you can't even handle the practice questions, right? So that is your underfitting. The bias variance trade-off, which I'm talking about, bias means your error from simplification, right? Bias means, let me write it down. If bias is your error from simplification. Okay, so when you error from simplification, what is happening? You are ignoring your real patterns, right? Then you are looking at variance. In variance, there is error from overreacting to small fluctuations in the data. Okay. Variance is error from overreacting to small fluctuation in data. Now, what is bias variance trade-off? Please understand, we want a model that balances both, right? So if you have underfitting, you have high bias, low variance, which is bad. Because why it is bad? High bias, low variance, because you are missing your patterns, right? Missing patterns. If you have overfitted, which means low bias, high variance, this is also bad. Means too noisy. We don't want that. What do we want? We want medium, just right. Medium bias, medium variance, because that is the best generalization. In financial world, if it is too simple, you miss the alpha opportunities. If it is too complex, you chase the noise. Best model capture your true signal without reacting to your every kind of blip or noise, right? So always remember that you have to have a very simplistic kind of understanding that you want a medium kind of bias, medium kind of variance. From the FRM exam, please understand, in your risk management and your trading models, overfitting can give you false confidence, while underfitting can miss your massive risk. You need to have your cross validation, test out of sample performance, apply your regularization techniques, which are lasso rich, to reduce your overfitting. Always check for your economic logic, not just for your statistical fit, right? So all these things you keep in mind, even though it is not given here, but it is, in other chapters, other topic, it will come. So please understand, overfitting means too complex. Basically, you are memorizing everything like a book, but you good doing good practice tests, but you don't do good in your real exam. Underfitting is, it is too simple, misses your signal, high bias and low variance. Good model is balancing between the two, bias variance trade-off, right? So remember that. Okay, moving on, guys. Next part is very important, guys. These kind of small question comes in exam. Okay, underfitting, overfitting. That's the example. It has been given here. Please understand, right? The optimum model complexity. You see yourself, right? Optimal model complexity has been highlighted here. You don't want high variance. You don't want your high bias, right? You want both of them to be lower, right? So optimal is in middle, right? Not on the sides, right? So remember this slide. And then we move to the next part. Okay, next question is the predictions that are generated from an underfitted model, right? Underfitted model was what, guys? Tell me. Underfitted model was what? Underfitted model, your noise was less, na, low variance, high noise, right? Both things are not high, both things are not low, right? One is, but now because it was one high, one low, na. So variance is basically noise. When you are underfitted, your noise is less. Low variance, high noise, right? See, right? Low variance, high noise. Remember this, guys. Variance is noise. So underfitting, noise will be less. Low variance, high bias, right? So an underfitted model, and your underfitted model excludes relevant factors and fails to capture relevant pattern. As a result, the prediction generated from such a model will have low variance and higher bias. Okay, so that's what we have here. And then we move ahead, guys. Okay, next is again a typical kind of topic. We are talking about now your training, validation, and your test data subsamples, right? So again, right, we are trying to understand this in very simple terms, right? The purpose of doing your training, validation, and test data subsample is, please understand, we are trying to test the fitted model by keeping part of the data sample, right? Right. But we are trying to test the fitted model by keeping part of the data sample out and see how well it predicts your unseen observation, right? Okay, this looks very difficult to understand, but in simple way, if I say that why do we split your data? When we build a model, we don't want it to just memorize the past, right? That's not the objective, right? Memorization is not the objective. Training on the past data set is objective. We want it to work well on your new unseen data. So we decide that we will divide data into three parts. One is your training data, one is the validation data, one is the testing data, right? We don't want memory, right? So training data, if you think of it, think of this as a practice material. The model studies this data to learn your new patterns, your estimate parameters. Think of it like teaching a risk model, your historical loan data, so it turns how your credit score relates to default. Then after training the data, you move to your validation, right? Validation is different. Validation is like taking a mock exam, right? You take a mock exam, you use to tune the model or compare different version, model A versus model B. It helps decide which model generalize better before you finalize. And once you have chosen the best model, you stop using the validation test because you don't want to you don't want to have cheating, right? So you stop it, you avoid cheating. And finally you have the test data, right? This is the real exam, completely unseen data, only used once at the end of check final model performance, right? You want to check the final model performance. If the model also performs well here, it's a good sign, it will work in the real world, right? So that's what is the training, validation, and test, right? Once it is training, then it is validating, and then it is doing your testing, right? So that's what is the whole idea. Training, validation, and test. This is what we are talking about. Training is generally your 2/3 of the data is training, 2/3. Your validation is 1/6 of the data, like 15, 20%. And test is also done on 1/6 of the data. So 1/6 is 1/3, right? Exact split can be very different, guys. Exact split can be very different. Each split can vary depending on your data size, but the idea is the same. Please understand, if we have to put in a very simple term, training is like studying for your exam, right? Validation is like your mock testing to test or choose your best strategy. Test is your final exam to see if you really have learned it or not. In FRM terms, this is all about your avoiding your overfitting, ensuring that model generalizes well, works not only on your in sample but also on your out of sample data. Okay, keep that in mind very, very clearly. All right, so that's what we have. And then the next part. Now the next part is the continuation of the same thing, right? We are uh, understanding the same thing again, right? When we're trying to understand the same data, the objective is very similar. The objective is to understand this part also in the same way as we understood the previous version, right? So that's what the objective is. Here we are talking about your, again, different data, cross sectional data, time series data, larger data set, smaller data set, k-fold cross validation, etc., etc. Okay, so we'll do it one by one just to give you an idea, so that you have an understanding, right? You have a typical understanding, right? Please understand that different data types have different splitting rules, right? So that, let's say you take the cross sectional data. When you take the cross sectional data, what is the cross sectional data? Let's say customer risk score, you have your loan defaults at one time. So, right, in that case, there is no time order. You can randomly split into your training, validation, and test. But if you're looking at your time series data, right, where stock prices or credit spread, right, if you're doing that, right, that has a kind of a natural order, right? When I say natural order, you must respect the time flow. You should use earlier data for training, then later data for validation, then the most recent data for test. So the two things here, right? Cross sectional data, there is no time order. You don't have to follow a particular thing that, okay, this data is for your training, this is for testing, this is for validation. But in time series data, there is an order, right? You have to have that. You must respect the time flow. Earlier data for training, later data for validation, and the most recent for your testing. You must, or you never peek into the future, right? Then you look at the large versus small data set, right? When you look at the large versus your small data sets, large data sets easier to split cleanly, right? That's what it is. There is a risk of improper allocation, right? Risk of improper allocation is low because you have enough data in each bucket. There is a small data set. Splitting reduces too much data from training. That's what, when we use cross validation. Then there is a k-fold cross validation, right? K-fold cross validation, right? When you talk about k-fold, so cross validation, what is the idea behind k-fold cross validation? The whole idea is, instead of fixing one validation set, we rotate the validation set multiple times. You have different processes. You divide your data into k folds. Let's say k is equal to 10, k is equal to 5. When you take k to 10, each is like 10%. You train on 9 parts, you validate on the 10th, you rotate. So each fold kind of serves as validation once. You average the result across folds. Why do you want to such kind of thing? Because you are using all data efficiently for both your training and validation, right? So that's the whole objective, right? It's a very, you kind of specific kind of exercise you do. Why do you do such kind of exercise? Because you're using all data very efficiently for both your training and validation. Okay, so example is k is equal to 10, right? Which we took, each observation you use 9 times for training and 1 time for your validation. Okay, so and then we have something called your leave one out cross validation, right? Leave one out cross validation means it's a special case of k-fold where k is equal to your n number of data points. Each observation becomes its own your validation set once. It's a very thorough, but computationally it is very, very, very heavy, useful for very small databases, right? So think of it as this kind of thing, difficult, right? Computationally, this method, last method, computationally very heavy, computationally very heavy, used for small data set. Okay. From the FRM perspective, please ensure that you know that model validation is robust, not just lucky on one split. Especially important in your small financial data set, which are like rare default, your stress events. In time series, this model always respect natural kind of ordering. Time series is very important. Train, validate, test in your chronological order. Overall, please understand, if you're looking for your cross sectional data, it can be a random split. If you are looking at time series data, it has to be split by time. The earlier data has to be used for training. The next data has to be used for your validation. The last data has to be used for, latest data has to be used for your testing. Small data set, you use k-fold cross validation, rotate your validation. Then there is leave one out cross validation, the last part which is given here, leave one out cross validation. Here each data point gets its turn. So that's what we need to remember. Again, a very theoretical kind of topic. Please understand. Okay, so this is what we have now. The question here is that an analyst is choosing between two machine learning models. Which of the following data set will the analyst most likely use to make the determination of which model to select? Right. Okay. So what is the answer here, guys? Which of the following data sets will the analyst most likely use to make the determination of which model to select? So will it look at the test data, test set, training set, variance set, validation set? There is nothing called variance set, right? It is test, training, and validation, right? So choosing between two machine learning model, which of the following data set will the analyst most likely use to make the determination of which model to select? Anyone, anything here, guys? What do you think? What can be the answer here, guys? Little tricky, right?
Validation.
Why validation? I'm just asking, right? I'm not saying is it right or wrong. What I'm saying is, any logic of this?
To check whether it is working. I mean,
Okay, okay. Why not something else, right? Hmm? Why not something else? Like any particular reason? If other thing is not important or this thing is more important, like what can be the reason? Right? See, validation data set is right. Validation data set is used to decide between your different machine learning models. The test set kind of determines the effectiveness of the model. Once it is already chosen, the training set is used to estimate your model parameter. Right. So each thing has a different use, right? So test set is for effectiveness. Training set is to estimate the model parameter, right? Please note it down. Test set is your model effectiveness. It is to check the model effectiveness, right? And then once you have tested the model, effectiveness of the model, which has already been chosen, right? The training set is used to estimate your model parameter, right? It is training set is for estimate model parameters. Okay, model effectiveness of chosen model effectiveness. So it means, right, validation test is for determination. Determination of which model to select. Okay, so answer is D. Again, remember, guys, one is for chosen model effectiveness, another is training set is estimate model parameters, third is for determination of which model to select, right? So D it is. Okay, remember that. Yeah, that is it. The validation test, that this is what we are talking about. Validation data is used to decide between the alternative machine learning models. The test set determines the effectiveness of the model once it is already chosen. The training set is used to estimate model parameter. There is no such thing as a variance set. Okay, let's move ahead, guys. Okay. All right, guys. Now we are moving into the last part, which is again very, very complex. So we'll be able to complete, I think, next 25-30 minutes. So that's a good news. Here we will get into your reinforcement learning and natural language processing, NLP and reinforcement learning, right? That's where we have to enter. So yeah, so let's get started, guys. Very, very complex algorithms, methods in your machine learning. Okay. The first part is reinforcement learning. If you remember, we studied reinforcement learning at the starting of this topic, right? When we started reinforcement learning at the starting of the topic, what were we doing, right? What exactly we said there, right? In that part, we said that unsupervised learning is for label data. Sorry, supervised learning is for label data. Unsupervised learning for your unlabeled data or you're finding the data structure. Reinforcement learning was something else. Reinforcement learning was all about decision making and rewarding and penalizing when you get the decision right or wrong, right? So the core idea here is reinforcement learning is your learning. It's a learning by trial and error, right? It's a core concept here is you are learning by trial and error. If you get it right, you're rewarded. If you get it wrong, you're penalized. An agent interacts with an environment, takes an action, gets a reward, good or bad, learns to improve decisions over time. It's like a trader who is testing his strategies, try something, see profit and loss, adjust. The key ingredients which are given here are that you need to understand the state, you need to understand the action, you need to understand the reward, right? So state, action, and reward, three things which are very, very important to understand. State, where are you right now? It is your portfolio composition, your market decomposition, your market condition. Action is decision you take. You decide to buy, you decide to sell, you decide to hold, you decide to hedge. And reward is feedback from the environment, which is the profit, reduce risk, higher Sharpe ratio, whatever, right? So this is what we have. So you need to understand this part. Mechanisms involve a systematic trial and error approach, similar to your computer learning to play games by playing against themselves. Then you have application in finance, derivative hedging, trading rules, managing large volume trades. Data requirement immense, requires large quantity of training data. Initial performance is weak but improves dramatically over time. Then there is something called Q value. See, Q value is your basically action value. It is also known as your action value, right? Q value is also known as your action value. When I talk about Q value, action value, Q value is expected reward of taking action in a given state. Formula is equal to your VS is equal to max AQSA. We don't need to bother about formula. Think of Q value as a scorecard for your possible action, right? Then it is decision making. When I talk about decision making, what do I mean? Basically, when you talk about decision making, it is your exploitation. When I say exploitation, exploitation means do what you already know works best, right? Then it is exploration. Exploration is try a new action, maybe they lead to better rewards, and then you try to balance both. When you say balance both over time, the algorithm shifts more to exploitation as it learns to what you already know your best. So overall, you need to understand is a trading algorithm might try new hedging strategies, your exploration, but mostly stick to ones it already found profitable or exploitation, right? So you try, you in between, you keep trying exploration, but you will stick to your exploitation more, right? Please understand, new action you will go in between, but generally you will stick to your exploitation, right? So what are the application in finance? Application in finance, there is derivative hedging. You learn your hedging strategies, not just your static delta hedging. You look at the trading rules, you adapt your trading bots that learn from different signals which work best. You look at the execution of large order, decide how to split your big trades into smaller one to minimize your market impact. So do all those things, right? So it's a good thing. You need a lot of data, you need a lot of learning curve, you need many trials. You have to start with weak things. You start with bad decisions early but improves with practice. It's like a junior trader who is making mistakes, but eventually you are learning your good strategies. Please understand very, very clearly that reinforcement learning is by learning by trial and error, learning by doing. So your state, your action, your rewards are the most important things. You also need to keep a track of your action values, key values, your balance, exploration versus exploitation, and it will improve over time, right? That's how it works, right? So it will improve over time. And next part is now we are getting into the deeper stuff, right? We are looking at your reinforcement learning, and we are trying to understand that again. uh, See, the objective here is the same as we did earlier, right? Objective here is not to focus too much on formulas, but objective here is to understand the theoretical background, because generally in FRM, especially nowadays, the exam, how it comes is the focus is more on the conceptual understanding, right? So we'll focus more on conceptual understanding in a very, very simple way. That's what we are trying to do, right? So here, first, we are trying to understand is what are your different methods to evaluate your action. When I say different methods to evaluate your action, please understand. We start with the Monte Carlo method. When I say Monte Carlo method, what we need to understand in this part is that when you talk about your Monte Carlo method, right, the idea here is you learn from the entire sequence of your trial, right? You take an action, wait until the end, then update based on your uh, total reward you got, right? It's like at the end of the trading days, how much profit did I make overall? And once you have done that, let me adjust my strategy based on the overall profit I made. So basically what you're using is you are using your full information, right? And then you are at the end of the day, you are updating or you're learning on the basis of the full information. What's the problem in this kind of system? The problem in this kind of system is that you must wait till the episode or in the day ends, right? It is not useful in a very long or ongoing process, because the long or ongoing process will end after many days, right? So that's not very useful, right? So you need to have that idea very clearly. Then we have something called your temporal difference learning, right? Temporal difference learning, the idea is different. You learn step by step as you go, not just at the end. So it's very different, right? It's a better way, right? Monte Carlo, because here learning is happening faster. Monte Carlo, the learning was happening at the end of each step. So longer time step, there was a problem. Temporal, the learning is happening as you're going, not just the end. So you looks only one move ahead, current reward plus estimate of future value. It's like, after this trade, I got some profit and my portfolio is a new state. Let me update immediately rather than waiting till the end of the day, right? Pros is that you have faster learning, works in continuous process. Cons is that you only look at one step ahead, so sometimes it is less accurate than your Monte Carlo. But temporal difference learning is the method behind your Q learning, one of the most popular reinforcement learning algorithm. One of the most popular your reinforcement learning method is your Q learning, and temporal difference learning is behind that method, right? So please remember that, right? And then we look at the deep reinforcement learning, right? Deep reinforcement learning. When I talk about deep reinforcement learning, please understand the idea here. Idea here is that instead of storing every state action pair in a giant table, you keep on adding the values, right? What you do is that you don't store it, right? You it is impossible for real world finance. You use a neural network to approximate your Q values. It's like you can't store every possible market share, so you will use a flexible function, which is deep learning, to estimate your which actions is best in any situation. This is how computers learn to beat humans at different games and your chess, etc. Right? These are applied to your trading bots. This is applied to your portfolio allocation. This is applied to your derivative hedging. So you are understanding my point, right? These are the advanced strategies, especially the reinforcement learning, which is what by how your hedge funds trade, right? This is how your HFT firms trade, right? These are the advanced strategies which are applied to trading bots and all those things. You can't store every possible market state, so you will use a flexible function, which is a deep learning thing, to estimate your which action is best in your which situation, right? In particular situation. From the FRM perspective, please understand Monte Carlo. When we talk about it, is more about learn at the end your full path. It is slow for the long processes. TD learning is learn step by step, which is ongoing, right? The ongoing learning step by step, right? The ongoing step by step. TD learning, right? Your deep reinforcement learning, you're using neural networks, right? You are using neural networks, and using neural networks when your state, your action space is too large. Okay. Overall, keep in mind that Monte Carlo, you learn from the full journey. TD, you learn as you go. Deep reinforcement learning, you use neural nets to handle the complexity, right? So numerical will not come from here, guys. More of a conceptual topic, right? All right, so let's do this question, guys. The question here is, an analyst applying a reinforcement learning model has assigned a probability to exploitation of 65%. As she completes more trials, she can reasonably expect that the probability will increase above what? 35% for exploration, 65% for exploitation, 50% for exploration, 50% for exploitation. Any idea, guys, what will happen here? As we go ahead, what will happen? Any idea, anyone? Look at it. Right now, the probability to exploitation is 65%, right? So if exploitation is 65%, exploration is what? Exploration is 35%, because adding both 65 and 35 gives you 100%. Exploitation is 65, exploration is 35. The key reinforcement principle: as trial increases, model learns more, exploitation increases, right? Right? As trial increases, model learns more, exploitation increases, exploration decreases, right? So if you look at this thing, I think your exploitation probability will increase above 65% for exploitation. Above we are talking about, na? It is not exploration, right? That will not happen, right? So exploration will not go. The probability of exploitation will go above, right? So that's what we'll have. So remember that exploration will go down. Right? This is what will reinforcement learning will choose between the best action already identified exploitation and new action exploration. Exploitation has the probability of P, which is expected to rise with additional trial. Exploration probability of my 1 minus P, and 2 expected to fall with additional trial. If the exploitation probability is already 65, the expectation is that it will rise as more trials are conducted, right? So that's what we have, guys. Then let's move ahead. Okay, next part. I think this is the last part we have for this lecture. Next part we have NLP, guys. This is the latest thing in your machine learning, where people want to understand in in simple way, and this is very very popular, right? In the AI space right now, natural language processing, right? Because natural language processing is what? It is a branch of machine learning, right? A branch of machine learning that helps your computers read, understand, and analyze your, what you say, human language, your text or your speech, right? So now we are using a lot of NLP models to, uh, you know, you know, the how do you think people trade when Trump announces something? Do you think people trade when Trump announces something by actually trading? There are bots. There are machine learning bots who are being processed on NLP. So they will keep track of words like tariff and I will harm this country, that, right? So they keep track of this word and then trade, right? If let's say there is a Fed announcement, how do you think the swings will go up and down when the Fed is announcing the interest rates are going up or down? Do you think somebody is there to trade manually? No, it's not that. There are engines, there are machine learning engines, natural language processing engines, right? So as soon as the Fed chairman starts speaking, it tries to analyze the voice of the Fed chairman. It tries to analyze how many times he is using rate cuts, or whether his tone is hawkish or dovish, and according to that the trades start happening, right? So it's a branch of machine learning that helps your computers read, understand, and analyze your human language, which can be text or speech. Earnings which come out of company, Apple earnings, Tesla earnings, the stock price immediately move. Do you think somebody is trading there manually? No, somebody is not trading there manually, right? These are the NLP machine bots which are working, right? It is also called your text mining. In fact, I have a very beautiful, very thick book, very thick, beautiful book I have from CFA Institute, which I can share in your group if you want. It's a very interesting book you can read. Not don't read right now. Maybe after your exam, I can share in your with your group. Right? It's a book on your how exactly NLP works, and or I'll say there's actually a 150 200 page book. The NLP is only one chapter. I'll say NLP also if you want. I'll share that book. It's a very interesting book. So in finance, in risk, it is like teaching the computers to read your financial reports, your analyst reports, your notes, your emails, your extract your meaning. And why do we use it in, especially in the context of FRM and finance? Because your fraud detection, right? You spot the unusual language in accounting notes. You look at the sentiment analysis. You judge whether the corporate statement, your news, your analyst calls are positive or negative. You do the categorization, classify the documents, your loan application into low, medium, high risk. You look at the keyword spotting, you detect the red flag words, default, going concern, etc. And then you look at the different benefits, right? You look at the benefits that there is definitely your speed, your consistency, your scalability, right? You're capturing the language, reprocessing, analyzing it. You're getting a lot of benefits, right? Speed, your document review, inconsistencies, etc. I told you about Trump statement, Tesla earning, right? All these things are there which are being used. Very interesting. And what are the steps in your NLP? You capture the text, you collect the data, you document your transcripts, your emails, your report, you pre-process text, clean and prepare it, you analyze, you run your machine learning model for the specific goal, your sentiment or your classification, your detection, right? You do that. And nowadays it is happening with videos also, guys. Even YouTube video influencers are using YouTube video. They're not preparing YouTube videos, AI is generating those videos, right? And then there's a text processing. There are key steps in text processing. They are like cleaning your data before analysis. There's a tokenization, which is a big project in HSBC which was happening. You break text into words or phrases. You remove the punctuation, your symbols, your lower cases, everything, right? You remove the stop words, right? Drop your filler words like the, is, and, that don't add any meaning. Then you have stemming. Stemming means that you reduce words to their root form but may not be real words. You're like arguing, argued, argues, argue, right? You do the lemmatization. Lemmatization is what? Lemmatization is that smarter than stemming, reduces words to their true dictionary form. Like if somebody is using verse, it means bad. If somebody is using argue, right, that is arguing, it use argue, right? And then there is n-grams. N-grams is look at the groups of words that appear together and carry your meaning, right? So overall, what you need to understand is that you try to capture, different things, right, in your system, right? You look at group of words that appear together and carry your meaning. And then from the FRM perspective, please understand risk manager must increasingly deal with unstructured data, your text, your speeches, your reports, your news. And NLP helps in your early warning systems, risk monitoring and fraud detection, etc. And then you look at your what you say, uh, your conceptual knowledge, right? Your conceptual knowledge is enough here. Know what tokenization is. Know what your stop word is, stemming, lemmatization, n-grams mean, right? So have that idea. Overall, what you need to understand here is that NLP is like teaching how machines to read. You should have clean text, your tokenize, your remove stop words, your stem, your L, lemma, n-grams, and analyze for fraud, sentiment, or classification. So that's what you do. Okay. The next part is again same thing, right? I think this is also very similar. I've already explained. There is a bag of word, right? Same thing we are talking about. There's a bag of word. Your processing text is considered a bag of words where word order and linkages, except n-grams, are irrelevant. The sentiment analysis, you use an inventory of sentiment words to assess if corporate news which has been released is positive or negative or neutral. So you use the your your sentiment, what you say, uh, you have your inventory, right? You use that. You count positive, negative, or neutral words. I told you, right? Fed speech, how many times he's using dovish, hawkish. Example: positive news, grow, relief, increase, rise. Example: challenges, handling positive words and negative connotation would have resulted in an increase. So if you have a confusing language, it becomes challenge. You need to do refinement, compare human reviews with algorithm reviews, and you need to do that. Right? Again, it's very straightforward. I think not very difficult to understand. Okay. Then we have a question, guys. Natural language processing (NLP) is used to evaluate the MD&A, management discussion and analysis. MD&A, which is given at the last part of the analysis of any report of a company's annual report. In removing the stop words, the NLP algorithm will remove all of the following word except, right, stop words. What, like, this is difficult, right? This is very English kind of thing. So what are the stop words? Stop words are, what was the stop word? Even I have forgotten, right? This what were the stop words, guys, which are considered stop words, right? This is, what are stop words? Hmm, do we have, what are the stop words? Uh, the, has, a, that have no other value beyond making sentences flow. That those are stop words, right? So guys, please remember this word. So I think uh, fallen is the only, or are, have, are making sentences. Fallen is the only thing is stock price fallen, etc. So I think it is D, right? D is the option. I think so, right? Maybe I am wrong. I think D is the answer. Yeah, D is the answer. Fallen, right? Because O, or, are, and have are like completing the sentences, right? Or are and have are considered stop words. Fallen is not a stop word. It has value in describing the direction of something, earning or sales, right? So with that, we have completed this chapter, guys. Very complex chapter. A lot of you would face problem in understanding this, but what you can go do and see, I have tried to make it very simple. But again, there are some things which cannot be made much simpler than required, right? So what you can go back and do is that you go back, try to have a revision, try to understand it well, right? Make some notes. I think that will be great, right? Few things are very easy. NLP is easy, right? PCA is easy, but so few things are quite difficult. Like your K means clustering is difficult, right? Underfitting, overfitting is easy. Right? Few things are easy, few things are difficult. So we have to make some notes. I have tried to give it you in a story format, so try to have that understanding. Please understand there is no numerical which will be coming from this part. The understanding, the conceptual understanding will be tested. Try to have that. Try to analyze that. If you try to build that, I think you will be totally fine. Okay. Any doubt? Anything in particular is troubling you? Nothing. All right, guys. Go back and revise, and then we'll see you next week. Okay. All right. Thank you.